Hello everyone, welcome to today's lesson. We will explore the application of common measuring tools together. In industrial production, measurement technology serves as a means for quality management, providing a technical guarantee for enforcing quality standards. To determine whether a part meets the required standards, measurements or inspections must be conducted. For commonly used measuring tools, it is essential not only to understand their structure and reading principles, but also to acquire the skill to accurately measure the size of products. Vernier calipers, squares, dial gauges, feeler gauges, and micrometers are typical tools for size and precision measurement. Today, we will focus on two commonly used high-precision measuring tools, the vernier caliper and the micrometer. By the end of this lesson, I hope everyone will understand the structure, reading principles, and measurement ranges of the vernier caliper and the micrometer. Additionally, I hope you will become proficient in using these tools for accurate measurements and correctly reading and recording the results. Next, let's officially begin today's lesson with the first section. The vernier caliper is a measuring tool that utilizes vernier readings. Its principle is that the n-1 division spacing on the main scale corresponds to the n divisions on the vernier scale. The difference between these division spacings is the least count. A vernier caliper consists of a main scale and a vernier scale that can slide along the main scale. The main scale and vernier scale of the vernier caliper are equipped with two pairs of movable measuring jaws, namely the internal measuring jaws and external measuring jaws. Internal measuring jaws are typically used to measure internal diameters, while external measuring jaws are used to measure lengths and external diameters. The depth gauge is connected to the vernier scale and can measure the depth of slots and cylinders. The main scale generally uses millimeter units, and the vernier scale features 10, 20, or 50 subdivisions. Depending on the subdivisions, vernier calipers are classified as 0.1 millimeters, 0.02 millimeters, or 0.05 millimeters calipers in terms of precision. The precision of a 10-division vernier caliper is 0.1 millimeters. The precision of a 20-division vernier caliper is 0.05 millimeters. And the precision of a 50-division vernier caliper is 0.02 millimeters. There are 3 steps to read the vernier caliper. 1. From the main scale, read the value of the 0 point on the vernier scale, denoted as A, in mm. 2. Identify the nth division line on the vernier scale that aligns with any division line on the main scale. Multiply n by the least count, u, which is determined by the type of vernier caliper. For a 10-division vernier caliper, the least count is 0.1 millimeters. For a 20-division vernier caliper, the least count is 0.05 millimeters. And for a 50-division vernier caliper, the least count is 0.02 millimeters. The value measured by the vernier scale, B, can be calculated as B equals n times u, millimeter. Calculate the final measurement result. X equals A plus B, millimeter. Let's take an example of reading the vernier caliper. Step 1. First, read the main value from the main scale, which is the value on the main scale aligned with the 0 mark of the vernier scale. In the diagram, the reading from the main scale is 7 millimeters. Step 2. Next, find the nth division line on the vernier scale that aligns with a division line on the main scale. In the diagram, the fifth division line of the vernier scale aligns with a line on the main scale. The vernier scale is a 20-division type, with a least count of 0.05 millimeters. The value measured by the vernier scale is calculated as 5 times 0.05 is equal to 0.25 millimeters. Finally, add the reading from the main scale to the reading from the vernier scale to obtain the total measured value. 7 millimeters plus 0.25 millimeters equals 7.25 millimeters. Next, let's learn about micrometer. The micrometer, also known as a screw micrometer, micrometer gauge, or micrometer caliper, is a tool that measures length with higher precision than a vernier caliper. It can achieve measurements accurate to 0.01 millimeters. Its measurement ranges typically include 0 to 25 millimeters, 25 to 50 millimeters, 50 to 75 millimeters, 75 to 100 millimeters, and 100 to 125 millimeters, among others. The micrometer can be used to measure internal diameters, thread pitch diameters, gear module lengths, or depths. The structure of an outside micrometer consists of the frame, anvil, spindle, fixed sleeve, knob, fine adjustment knob, thimble, locking screw, and insulation plate. On the micrometer, both its accuracy and measurement range are marked. The micrometer shown in the diagram has an accuracy of 0.01 millimeters and a measurement range of 0 to 25 millimeters. The working principle of the micrometer is based on the micrometer screw mechanism. The fixed sleeve, 5, marked with lines for a length of 0 to 25 millimeters, is divided into 50 equally spaced divisions on the thimble, 6, which is coaxial with the micrometer screw, 3, that has a thread pitch of 0.5 millimeters. The measurement value is obtained by reading these divisions. During measurements, every complete rotation of one division on the thimble corresponds to an axial displacement of 0.01 millimeters for the spindle. Before using the micrometer, check the 0 position. Rotate the fine adjustment knob slowly to bring the spindle into contact with the anvil until the ratchet clicks. At this moment, the 0 mark on the movable sleeve should align with the reference line on the fixed sleeve. Otherwise, systematic measurement errors may occur. After calibration, hold the frame with your left hand and use your right hand to turn the coarse adjustment knob, widening the gap between the spindle and the anvil slightly larger than the object to be measured. Insert the object between the spindle and the anvil, and then rotate the ratchet until the object is securely clamped and the ratchet clicks. Use the locking screw to fix the spindle and proceed to read the measurement. Steps to read a micrometer. First, read the largest value displayed on the fixed sleeve. Then, read the marking on the thimble that aligns with the reference line on the fixed sleeve and multiply this value by the least count. Lastly, add the two readings together to obtain the total measured value. It is worth noting that the micrometer requires one digit of estimation beyond the least count. Therefore, the third decimal place is the estimated value. Example of micrometer reading. Step 1. Read the maximum value displayed on the fixed sleeve, which is 8.5 millimeters. Step 2. Read the marking on the thimble that aligns with the reference line on the fixed sleeve, and then multiply it by the least count. In the diagram, the value shown is 6 times 0.01 millimeters equals 0.06 millimeters. Because micrometer readings require estimation to the third decimal place, even if the zero marking of the fixed scale aligns perfectly with the movable scale's markings. The thousandths place must still be recorded as 0. Finally, combine the readings. 8.5 mm plus 0.06 mm equals 8.560 mm. In industrial manufacturing, even a minor measurement error can lead to the stagnation of an entire production line or serious quality issues. For instance, in an automotive manufacturing factory, a dimensional error in a single part prevented it from perfectly fitting with other components, ultimately affecting the overall assembly quality and performance of the vehicle. This incident not only caused significant economic losses for the manufacturer but also severely impacted the company's reputation. This case reminds us that every measurement step is critical in industrial manufacturing. We must always maintain a high sense of responsibility and meticulous attitude to ensure accurate measurements. Please analyze the reading of the outside micrometer in the diagram provided. Through this lesson, we gained an in-depth understanding of the structure, reading principles, and methods for using vernier calipers and micrometers. We mastered the steps for reading these tools. More importantly, through case studies, we deeply understood the importance of scientific thinking and meticulous attitudes in industrial manufacturing. I hope everyone can proficiently use these tools in your future studies and work, contributing to ensuring product quality and supporting the development of China's industrial manufacturing industry.